Good morning, guys. Today we are going to discuss about the built-up columns, and as in yesterday that we have discussed the lacing system for the built-up columns. We have discussed what are the lacing systems, which members are used as lacing systems, what is the need of providing a built-up columns, what are the general systems of built-up columns provided, that is the lacing system and the Batten system. Then we have shown some, we have seen some pictures of the lacing system and the Batten system. Then we have discussed about how to design a column based on the lacing system. There are some numbers of steps. Finally we have calculated what is the design of the lacing system, how to design the lacing system. At the last step, that is the design of the end plate, we have told that the end plate will be designed as per the design of the Batten plate. So today our discussion will be based on how to design a Batten plate system, that is another type of built-up column system for our study. Now when we are discussing the Batten system, first, what are the battens? Battens are the plates or other rolled section used to connect main components. So battens are the plates member which is used to connect two channel or to four angle section to act as a compression member. The numbers of the battens should be such that it is divided it divides the member at least three bays. That means the numbers of the battens, consider these are the battens, okay. So the numbers of the battens should be such that it divides the whole member. If this is the whole member, consider this is the whole member, okay. The number of the battens should be such that it divides the member into at least three parts, okay. At least three parts it should divide on, okay. At least three parts, at least three bays it should divide the member, okay. Now there are two type of batten plates are available. The batten plates which are provided at the centers are called the intermediate batten. The batten plates which are provided at the center are called the intermediate batten, and the batten plate provided at the end are called the end batten, okay. End batten. They are generally designed in a similar way, but the procedure is somehow different, okay. So you will see throughout our study that how to design the batten plates. Now the design, first are the design step. Now the batten plates is a normal built-up column system, so it is also designed in a similar way as in the case of laced column. Only difference is that in case of the laced column, that we see in case of the lacing system, the slenderness ratio for the laced column, the slenderness ratio for the laced column is generally taken as 1.05 times of the KL by the most unfavorable slenderness ratio. That is the maximum slenderness ratio for lacing system. Only difference in the Batten system, the slenderness ratio is, in case of the Batten system, the slenderness ratio is taken as, it is been specified here that in case of the Batten system, the slenderness ratio is taken 1.1 times the most unfavorable slenderness ratio. So there is a first difference is that the slenderness ratio to be 1.1 times the most unfavorable slenderness ratio, that is the maximum slenderness ratio of the column. So this is the first step. So from the step 1 to step 7 in the lacing design, the lacing system design will be followed here also, because up to step 7 what we have developed in the lacing system, that is how to design the column, that is the how to select the member from the SP6, and then we have discussed up to step 7, that is we discussed up to step 7, that is what is the slenderness ratio, and if the load that coming to the column is and the strength of the column is sufficient to withstand that load. So this is step 1 to 7 will be followed here also. Now coming to the after step 7, in the similar way as in the case of the as in the case of the lacing system, the spacing of the two members will be selected. Now, if there are two channels placing back to back, if there are two channels placing back to back like this, for that this formula will be provided, and for that this formula will be provided. Okay, now if there are four angles that are connected together, the formula will be somehow different. If we go through that math, then we will discuss. Okay, so generally these two formulas will be used. Okay, now after this is under the at this step will be under in the step number 7. So here we are determining the spacing of the two channel members or angle members or two channel members. Now coming to the design of the batten plate. So step number 8 now we will discuss. As per the code, the maximum spacing of the batten plate will be the spacing of the batten shall be as per the code clause 7.7.3. As per the clause 7.7.3, the spacing of the batten shall be such that the slenderness ratio KL by R of any component over that distance shall be neither greater than 50 nor greater than 0.7 times the slenderness ratio of the member as a whole. That means there are two things. Number one is that formula, that is the 0.7 into KL by R, that is given here, 0.7 into KL by R, and the second one is C by RY, that is the any component, that is the slenderness ratio of the any component, that is the C by RY. C by what is the what will be that? The center to center of its end fastener shall be in the spacing of the batten. So the C by the maximum spacing of the batten should be calculated in such a way that the minimum slenderness ratio of the component member C by RY is not greater than 50 or 0.7 times the slenderness ratio. So C by RY is the the slenderness ratio of the batten plates, because C is the spacing between the batten plates. C is the spacing between the batten plates that we do not know. The C, that is the spacing between the batten plates. This is the C. We do not know the spacing between the batten plates. So the C divided by RY. Why it is RY? Because C by RY. So C by RY should not be greater than 50 or 0.7 times. So this formula is another one formula, and this formula is another formula. So by this, considering these two formula, we have to determine the spacing of the channel, because KL by R of the total member that we know we have calculated in the previous stages. KL by R, that is the slenderness ratio of the member, and from that, and RY, that is the RY for the member, we can get it from the SP6 value. So C by RY should be less than these two values. So from here we can calculate the value of the spacing of the batten plates. Now coming to the design of the batten plates. The section of the batten plates are selected as follows. Now we have to select as trial section of the batten. Now how the trial section of the battens are generally selected. Okay, how the trial section of the batten are generally selected, that we will discuss now. Batten thickness as per clause 7.7.2.3. where is that? 7.7.2.3. this is the size of the batten plate. Okay, as per the clause, minimum thickness of the batten plates. Okay, the minimum thickness. Now coming to that, the minimum thickness of the batten plate, the thickness of the batten or the tie plate shall not be less than 1/50 of its distance between the innermost connecting line of the rivet, bolt or weight. That means the T minimum shall not be less than the T minimum, the minimum thickness of the batten plate should be greater than S by 50. Okay, that is the 1/50th of the distance between the innermost connecting line of rivet. So what is the innermost connecting line of rivet? That is the S. What is the meaning of S? S means S plus 2G. That is the S. From innermost, this is from here to here. So this is the S, that is the innermost distance, the distance between the innermost bolt. So this is S. So what is the meaning of S? S dash plus 2G, where G is the gauge distance taken from the IS handbook. So if we go in the IS handbook, if it is a normal channel section, we can get the G value from here. So from here we can take the G values and put it here to calculate the T minimum, that is the minimum thickness of the batten plate. Okay, now coming to the batten depth. Now the depth of the batten plate, the intermediate batten. Now there are two type of batten. Number one is the end batten and the number two is the intermediate batten. So now what is the effective depth? The batten depth. Now the intermediate batten shall not be that. Here it is written that the intermediate batten shall have an effective depth not less than 3/4 of this distance. Okay, shall have a 3/4 of this distance, and the end batten, that is the end batten, and the end batten shall have an effective depth. So the end batten shall have the end batten shall have an effective depth not less than the perpendicular distance between the centroid of the main member. The centroid of the main members means the CG of the main members, that is the CYY. The CYY values are also taken from the ISSP6, can be taken. So if you see in the ISSP6, this is the value of the CYY. Okay, CXS and CYY. This is the value of the CYY that we can take from here. So here, so CYY is given here, center of gravity value. So D aid will be should be S dash plus the CG distance from the, as per the code, the CG distance taken from the handbook. And for the intermediate batten shall have an effective depth not less than 3/4 of this distance. So 3/4, that means 0.75 of the D end, that is the D end means the effective depth of the end batten. So the effective depth of the end batten and the intermediate batten are as per the code, that is the, for the end batten the value of the effective depth will be the distance between the center of gravity of the two members, that is the first the spacing of the two members plus the center of gravity, that is the 2 into CYY. Why it is 2? Because the center of gravity of the two members, that is 2 into CYY. And for the intermediate batten, the value of the effective depth would be the value of the end batten effective depth into 3/4, that is the 0.75. Now in no case, but in no case, it is for the generalized case, for in no case shall the effective depth of any batten be less than twice the width of one member. That means twice the width of, so one member twice the width of one member. So consider there is we are taking the member to be an IS LC 200. So the width of the member, that is the width of the flange, that is equals to 65. So if we use that member, the D in all case, so if for end for effective, it should not be less than 2 into the width of that member. So in case of the ISMC, that ISMC 65, if we use our section to be ISLC 75, it should not be more less than 2 into B, that is the 80 mm. So this is in no case that value has to be achieved. This is the batten depth. Now coming to the forces in the batting. What are the forces that are coming to the batten plates? Now batten shall be designed, this is the step number 10. The batten shall be designed to carry the bending moments and shear force arising from the transverse shear force Vt equal to 2.5% of the total axial force on the whole compression member. So we know the what is the total axial force coming to the whole compression member, that is the Pu. So if you know the Pu, then the total transverse shear force coming to the batten plate will be equals to 2.5% of the Pu that we know. 2.5% of the Pu will be the transverse shear force as per the code value. Now this transverse shear force will cause longitudinal shear and the bending moment. Shear force and bending moment, it will cause the transverse shear force. So the longitudinal bending moment that will be caused. So the batten shall be plates angle section to resist simultaneously a shear force and the bending moment, that is the Vt into Vt. Vt is the transverse shear force. So transverse shear force we have calculated Vt. So the transverse shear force will cause the longitudinal shear force and the moment. So the longitudinal shear force will be Vv into Vv is equal to Vt into C by Ns, Vt into C by Ns. Okay, then step 2 is required cross sectional area is calculated. So we are calculating required cross sectional area will be 7714.3 millimeter square. Now from the IS handbook, let us take a section compromising of two channels so that the total cross sectional area is greater than or equals to 7714. Let us take a section. Okay, so two channels back to back, we have to check the section. So which section we choose check? I am ISLC 300. ISLC 300 having an area of 4211 millimeter square. So if we multiply it with 2, we are getting 8422 millimeter square, which is much more greater than, which is greater than the 7714.3. So it is okay. All the properties are written here, RZ, RY we know. Now coming to the step 4. Okay, now coming to the step 4. What is step 4? That we have to provide RY greater than RZ. So RZ will be R mean. So the value of RZ is 111.98. So RZ is equal to R mean is equal to 111.98. So the effective length of the column. Now what will be the value of the K? So coming to the code again, coming to the code. Okay, the beams, the column is restricted in position but not in direction. So position it is restrained, but not direction it is not restrained. So position it is restrained and direction it is not restrained. So for that, so for position, that is it is restrained in position, that is translation, and not in direction means rotation is free. So the value will be 1 into L. Okay, so taking the value of KL is equal to 1.0, getting the L effective at KL by R we are getting. So R will be R minimum. So at that value for last column, now for last column, the value of will be taken as, for last column the value will be taken 1.05 times, putting the value here, putting 93.765, which should be less than the maximum slenderness ratio, that is 180 we know. So for that value and buckling plus C for rolled channels, always for rolled channels, section, always any it is equals to C. Okay, for rolled channel section or for built up section, always the value is C. So taking the value to be true and taking the values, we are getting a FCD will be equals to 115.73. Now step 7, that is we have to calculate the, from step 7 the design capacity. The design capacity will be equal to 974.67, putting the value AE, that is FCD, and that is AE that we have calculated. So it is less than that. So the design has failed, the failure has occurred, the design has failed. So we have to redesign the section. So taking some higher value than that, taking an higher value than that, taking a higher value, we am taking higher value, that means taking ISMC 300. I have 300 having a sectional area 4564. The total area provided is equal to 9128, which is greater than A. Which is greater than A. So assuming ISMC 300 with all the properties are written here, IZ, IY, all the properties RY, RZ are also written here. So now coming to the providing, now coming to the steps. So first step is to RZ will be R minimum, taking the RZ to be R minimum. Similarly, step 6, we have calculated the KL, K will be 1. Similarly, 88.91, buckling class C, FCD 126.65. Okay, now step 7, design compressive stress. 7 is 1119.55, which is greater than 1080. So this design is now safe. Now coming to the design procedures. Now for after step 7, we have to determine the channel spacing of the channel. Now spacing of the channel is calculated for two channels back to back, as we are taking the channels, two channels, where is my two channels are back to back. So for spacing, two channels are back to back, this formula to be taken. So providing this formula, putting the all the values IZ, IY, CYY, the CYY value is also written here, I think CYY is also written here. 23.6 it is written here. So putting all the values, we are getting S equals to S by 2, S equals to 183.1, taking the value to be 184 millimeter. So let us provide the channel at a spacing of 184. So S equals to 184 we have got. Now step 8, angle of inclination. So providing an angle of inclination, if it is initial value to be 45 degree to be taken, so we are taking a 45 degree. Now coming to the spacing of the, coming to the step number 9, that is coming to step number 9, that is the spacing, that is the spacing of the lacing bars. Now how to calculate the spacing of the lacing bar, that we have calculated. The spacing of the lacing bars will be equals to that value. So A, the spacing of the lacing bar, A1 is equal to spacing of the 2A by sin tan theta for single lacing, to A by tan theta for double lacing, and A equals to S plus 2G. So as we are using single lacing, so 2A by tan theta we will use, so A equals to S plus 2G, so S plus 2G equals to that value. Then putting the value of the spacing of the lacing bar is equal to that value, so 568 mm we are getting the value of the spacing of the lacing bar. Now as per the code recommendation, the spacing of the lacing bar should not greater than 50 or 0.7 times the most unfavorable. So the spacing of the lacing bar is equal to 568. Now this will be less than 50 or 0.7 times the most unfavorable slenderness ratio of the member. So it should be less than A1 by RY. So the ratio of the component member A1 by RY should not be greater than, so A1 by RY should not be greater than, A1 is the spacing of the lacing bar, should not be greater than 50, so its condition is proved. And also A1 by RY should be less than the 0.7, the most unfavorable slenderness ratio is 88.91 that we have calculated. So 88.91 we are putting the value, so hence okay, so both the cases are satisfied. Now coming to the step 10, lacing bar should be proportional to calculate VT equals to 2.5% of the axial force. So VT is equal to total axial force 1080, so the VT will be equal to 27,000 Newton. Now the transverse shear force, for each cases, so the transverse shear force for each cases will be, transverse shear force in each panel will be equals to transverse shear force in each panel will be equals to Vt by N, that is specified here, the transverse shear force in each panel equally, and the panel of also the Vt by N is the transverse shear force in which the lacing is subjected. So each lacing will be subjected to a transverse shear force Vt by N. So Vt by N will be equals to 27,000 by 13,500. Now coming to step number 11. So compressive force and compressive force for the either lacing bar is equal to Vt by N cosec theta for single lacing and Vt by 2N cosec theta for double lacing. So Vt by N. Now here N equals to 2. Why? What is the meaning of N? N means the 2 for 2 channel or 4 angle placed back to back. Here 2 channels are placed back to back, so N will be, value will be equals to 2 for 2 channel placed back to back. Similarly, compressive force in the lacing bar Vt by N cosec theta as per this formula. Okay, so Vt by N cosec theta for single lacing, so we are getting the compressive force in the lacing bar, that is equals to 19,091.8 Newton. This is the actual force in the lacing bar. This is the important value because lacing bar should have the strength to stand the force. We will check that in the later stages. Now coming to the design of the lacing bar. Now the width should not be less than 3 into nominal diameter of the end bolt. Now we have to assume some diameter of the bolt, considering the diameter of the bolt to be 20 mm dia 4.6 gauge bolt. In the math it is been also specified that the math is proportional with 20 mm dia, assume 4.6 grade bolts. We are assuming 20 mm dia bolt on which the lacing bars will be connected. So assuming 20 mm dia 4.6 grade bolts, so width of the lacing bar 3 into 20 is equal to 60 mm, providing 65 mm. Some extra value from that, so 65 mm for the lacing bars. Now thickness of the lacing bar should not be less than 1/40 of its effective length, and for double lacing system 1/60 of its effective length. Now we have to calculate the effective length. What is the formula for calculation of the effective length of the column? Now for single lacing system, effective length is A by sin theta, and for double lacing 0.7 A by sin theta. So A by sin theta is equal to, what is the value of A that we have calculated? A equals to 284, we know, so 284 S plus 2G. So effective length of the column is equal to S plus 2G A by sin theta. Sin theta means cosec theta. 1 by sine theta, 1 by sine theta we know equals to cosec theta. So putting the value of cosec theta here, so s plus 2g cosec theta, that is 10.004 meter. So thickness should be greater than 10.004 meter. So provide a 12 mm thick lacing bar. So we are providing a 12 mm thick lacing bar having a width of 65 mm. That we have calculated the width and the thickness of the lacing bar. Now coming to step number 13, the minimum radius of gyration of the lacing bar, r minimum t into root 12. So t divided by, so it is t divided by root 12. So 12 divided by root 12, that is 3.464 meter. Okay, now step number 14. What is step number 14? Is the riveted connection. Okay, the riveted connection, the L effective, that is the slenderness ratio, L effective by R minimum should be less than 145. So L effective that we have calculated, what is the value of L effective? That is, we have calculated this value, s by plus 2g cosec 45 degree, s plus 2g is equal to 284. So 284 cosec 45 degree, 284 cosec 45 degree by 3.464 is the minimum radius of gyration, that is equals to 115.95, which is less than, it should be less than 145. That also this condition is satisfied. Now coming to the step number 15 and 16 all together. The 15 number 16, this step state the design compressive strength of the lacing flat computed for the calculated value of the lacing flat should be more than the force in the flat and tensile strength of the flat. Now, what is the design compressive strength of the flat? PD equals to FCD into E, the compressive strength of the lacing bar for slenderness ratio. Now compressive strength formula is equal to AE into FCD. Now compressive strength in the lacing bar, we do not know the compressive strength of the lacing bar. We have calculated the compressive strength of the column but not the lacing bar. So we have calculated the compressive strength of the lacing bar. So what is the slenderness ratio we are getting here? That is 115.95 is the slenderness ratio of the lacing bar, and Fy is equal to 250 MPa and given and buckling class C. Now lacings are some solid members like this. So for solid members, buckling class is, for solid members, the buckling class is equal to, for all solid members, buckling class equals to C. So buckling class will be equals to C for solid members. Okay, so buckling class, putting the buckling class value of C for the solid members. So C equals to, for, so FCD from the code we are getting from the chart number C, chart number C, this is the value for buckling class C. We are getting the value for 115, that is from here, it will be from here 115.95. It will take the value, it will be between that. So we are getting a value of 88.2 by interpolation. So the compressive state will be now FCD into AE. What is the value of AE? What is the meaning of AE? AE equals to the length, the area of the what is that? Area of the lacing flat. So area of the lacing flat will be equal to 65 is the width of the lacing flat and thickness of the lacing flat is 12. So AE into FCD will be the length area of the lacing flat. So it will be greater than 19.09, that is the compressive force in the lacing bar. As per the code, it should be greater than the compressive force in the lacing bar. It is been specified that it should be greater than the compressive, more than the force in the flat, that is the compressive force in the lacing flat we have calculated. Similarly, the tensile strength will be, now it is a tension, so the tensile strength is determined by the cross section yielding and net section rupture. What is the formula for cross section yielding? That is the AgFy by gamma m0. We are getting that value. And for net section rupture, 0.9 B minus DH into T into Fu by gamma m1. This is the formula that is written here only for bolted section. So we are getting the value of B is equal to 65, DH 22 for 20 mm diameter bolt. So DH will be equal to 22, T is equal to 12 mm thickness, because of the thickness of the lacing flat is 12 mm, and Fu 410, we are getting a value of that. So the tensile strength is the lesser of that, it is the lesser value. So tensile strength is equal to that. Now coming to the step number 17. Step number 17 is step number 17. It is very important, design of the connection. So design of the connection we have to determine. So design of the connection, the design, that is the bolt and bolted connection. So here bolted connection, number of the bolts we need to determine, and also number of the bolts we need to determine, and also the bolt should have the bolt should be lacing bars connected at the same point. Then now we are assuming the lacing bars are connected with 20 mm diameter bolt at one point. So at one point the connection is there. So for one point the strength of the bolt in double shear, because why it is double shear, because if it is one lacing bar connected together with another lacing bar in a member, the bolt is provided here, so it will be 1 2 3. So if there is three member like that, one member, two member and three member like that, if the bolt is in this connection, so it is a double shear connection. Always in the shear in the bolt design we have discussed that. So the bolt the strength of the bolt in double shear, it will be because that value for 20 mm diameter bolt, this is the value of the double shear. Strength of the bolt in bearing, this is the formula for strength of the bolt in bearing. Now kb is the less of, there are some values, that is p0, we have to pitch, and we have to calculate the edge distance. We are not going to that much distance, we are taking kb is equal to 1. This is the final maximum value we can take, so kb is equal to 1, so it is getting 196.8. so the strength of the bolt is equal to 90.528. so the load coming to the bolt and rivet, the load coming to the bolt and rivet is equal to 2 into vt by n cot theta. So to the vt we have calculated, that is the vt value is, the vt is equal to, that we have calculated 27,000 is the value of vt, 27,000 is the value of Vt, that is the value of Vt 27,000. So 2 into Vt by cot theta is equal to 27,000 cot 45 degree, 2 cancel out, 2 cancel out, cot 45 degree is equal to 1, so it is 27,000. so number of the bolts equals to 1 nose. So provide one number of 20 mm diameter, 4.6 get bolt for connection. So this lacing bars will be connected with one number of 20 mm diameter bolt, it should be sufficient. Now design of the tie plate, this is the important part. Okay, so design of the tie plate. Okay, the column ends are fixed with tie plate provided at the, and will be designed as per the batten plates. Now coming to the design of the batten plates. Now these tie plates are provided at the end, so it will be designed as per the end batten, because end batten will be at the end tie plate. So if we are going in the end batten design, so it is the design of the end batten. So batten thickness T minimum will be greater than equals to this value. Batten depth for D end S dash plus 2 into CYY. So putting all the values here, so effective depth of the tie plate S dash plus 2 CYY, 184 plus 2 into 23.6, we are getting the value 2 into width of the members. So it should be greater than 2 into width of the member, so this is the 2 into 90, 180 mm. Now again, before this step the overall depth can be calculated. So overall depth will be equals to D into H, D end, that is the end effective depth of the end bars, end batten, plus 2 into H distance. Now for 20 mm diameter bolt, for 20 mm diameter bolt with normal holes, the minimum thickness, minimum edge distance taking is 33, we are taking 35, so it is the value of the, so providing 3110 mm overall depth of the batten plate. Now the thickness of the batten plate should be, minimum thickness should be S plus 2G by 50, that we have seen here, we have seen in the design of batten plate, that is the S plus 2G. the thickness of the batten plate should be S dash plus 2G by 50, it should be more than that. Okay, so S dash plus 2G by 50, it should be more than that, so it should be more than, so providing the batten depth S plus 2G, that is the by 50, that is equal to 184 plus 2 into 50 by 50, 5.68 mm is the, it should be greater than that, providing 8 mm. So now coming to the length of the tie plate, length of the tie plate equals to length of the tie plate. So if it is one member, but if this is another member, the length of the batten plate will be that value. So if this is S, if this is BF, that we know, so it will be equals to S plus 2 into BF. So 184 plus 2 into 90, 90 is the BF of this member. We know, we have got it from here, that for that value BF equals to, where it is if we see in the code, we can see the value for ISMC 300. For ISMC 300, BF is 90. This is the value of BF. So putting the value here, we are getting the end plate thickness to be 364 meters. So providing tie plate at the end of 364 into 310 into 8 mm. This is the very important math where channels are placed back to back. Now please let's try the math by providing channels toe to toe. This will be your assignment for today. Okay, this will be assignment for today, to provide the lacing bars channel toe to toe. Now coming to the another math for the design of the batten plate. Now for the here the effective depth is equal to 5.9. Effective length of the column is given, that is the K into L value is given. 2000 kilonewton is the effective amount of load, and channels are back to back, and side welding is used. So welded connection here is used. So first all the properties are written. L effective, F0, so step 1. Now coming to the design of the batten plate. Okay, now in this another window we have opened the design steps. Now from 1 to 7 follow the design of the column part. So design of the lacing bars will be followed from here to here. Okay, now in here the total axial force 1080. Where is math? Where is the math? Where is the math? Where is the math? Okay, so total assuming FCD. So we have to first assume the FCD values, that is will be equal to 125 to 175, providing assuming 170 MPa as the load value is some higher, taking the value of FCD is equal to 170 for F25. So required cross sectional area is equal to 11764.71 millimeter square. Now we have to provide two channel back to back, so two channels should have the required thick area for that load. So taking the two channels with taking the two channels having 11764. so if we take ISMC 350, that value, so it is 5365. so it is 5365. The total area provided is equal to, will be much more than that. If it is total area is equal to 2 into 5365, it is so the total area we are getting is equal to that. So step 4 in the design was to providing RZ is equal to R minimum. So providing RZ R minimum is equal to 136.66. Okay, so providing RZ R 136.66. Now effective slenderness ratio will be equals to 1.1, because here it is 1.1 times the actual maximum slenderness ratio. So 1.1 times the actual maximum slenderness ratio, that is equals to 59005 that is equals to 47.51. Now for lambda E is equal to atho, Fy is equal to atho, and class C, because channel section FCD is equal to 186. So the A into FCD is equal to much more than that. 2003.67 is equal to greater than 2000. So it is greater than that. So design is, we can proceed with the design. Now second, we have to follow the spacing of the channels. For channels back to back, this value will be taken. So S is equal to, we are getting the S dash or S dash here, we are getting value will be S dash 220 millimeter. We are getting the value of S dash, that is the spacing of the column is equal to 220 millimeter. Now step 8, what is the step 8? Maximum spacing of the batten should be calculated in a way that the maximum slenderness ratio of the component C by Ry. So C by Ry should be not be greater than that value and 50. So that value is equal to 0.7 into the 47.51, that is the most unfavorable slenderness ratio. So it will be greater than C is equal to 941.17, less than, it should be 1015. Providing a spacing of the batten is equal to 940 mm or less than 2, so the condition is satisfied. Now coming to the design of the batten plate. So there are two batten plates, one is the end batten, another is the intermediate batten. Now for the end batten, as welded connection, so as welded connection, there will be, as welded section is provided, there will be no requirement of the gauge distance. So this gauge distance will not be required as it is a welded connection. So this gauge distance we do not know, because the welded section are provided throughout the section. The welded are provided. Okay, so the gauge distance will not be required. So the effective depth will be equals to the overall effective depth equals to the overall depth of the batten plate, because S plus 2G, that is the effective S plus 2G effective depth equals to S dash plus 2 CYY. S dash means S plus 2G, so S dash will be equals to the total depth. So 220, as we are getting the S dash equals to 220, it will be the total value. So 220 plus 2 into CYY, so 268.8, that is 270 mm. Why? Because in case of batten welded connection, there will be no bolt, so there will be no requirement of the gauge distance. So S dash will be equals to the total S dash, so 220 plus this distance, so 2 into CYY, so is equal to 270 mm. Now thickness of the batten plate, what is the formula for the thickness? It should be greater than 1 S by 50, that is equals to S equals to here S dash plus, there is no need of 2G, so S dash plus 2G we do not need the 2G, so S plus 2G, so S plus 2G we are getting, so S divided by 50, that is equals to, should be greater than 4.4. as welded connection, no gauge distance, so providing T is equal to 10 mm, some higher than that, because when I have done the math, when I have practiced the math before this presentation, I have taken the T minimum is equal to 6 mm, but the design gets a failure, so we are providing T is equal to 10 mm. So length of the batten plate equals to, as we are now length of the batten plate, what is the length of the batten plate? Length of the batten plate will be, value will be equals to, as we are using welded connection, the length of the batten plate as per cos 7.7.4.1, the overlap of the batten plates of the main member shall not be less than 4 times the thickness of the batten plate, as per clause 7.7.4.1. Let's see the clause 7.7.4.1. The 7.7.4.1 clause states that when a tie plate or batten plate overlap the main member, the amount of the lap shall not be less than 4 times the thickness of the plate. That means if this is the batten plates, okay, if this is the batten plate, now if this is the batten plate, the overlap, this is the overlap, the length of the overlap should not be less than 4 times the thickness of the plate. So 4 times, so overall overlap of the batten plates 4 into 10 in 10.40, that is 4 into 10, that is equals to 40 mm, because 10 is the thickness. So length of the batten plate will be equals to, this is the overlap, this is the overlap, and this is the S dash, so S dash plus 2 into S dash plus 2 into providing 60 mm overall depth. It should be greater than that, it should not be less than, so greater than that, so providing 60 mm overall 60 mm overlap depth. So 220 plus 2 into 60, this is 340 mm, providing n batten is equal to that value. So providing n batten is equal to the, we have got the thickness, we have got the length, and we have got the depth. Now coming to the intermediate batten, the depth of the intermediate batten is equal to, will be equals to, coming to the design steps, the intermediate batten is equal to 0.75 into dn, so value is equal to 0.75 into dn, that is 205. So again this all will be repeated, overall batten depth will also be repeated, so 4 into 10, so thickness of the batten plates will be also same. Okay, so providing a intermediate batten of 340 into 205 into 10 mm, so difference is the depth of the batten. Now coming to the step 10. What is step 10? Step 10 is the batten would be designed to carry a bending moment and shear force arising from the transverse shear force. Transverse shear force 2.5% of the PU, so to transverse shear force 50 kN. So longitudinal shear VV is equal to VT into C by NSC is the spacing of the batten plate. Spacing of the batten plates we have calculated is equal to 940. So VT is equal to 940 is the spacing of the batten plate, that we know we have calculated it. Now putting the values here, VT is equal to 50 into 10 to the power is equal to value of the SF into VT, SF in VT into C divided by N. N is equal to 2 for always. I have told that for 2 channels and 4 angles, the value of N will be equals to 2 into S. S is the minimum transverse distance between the centroid of the rivet bolt weight. So minimum transverse distance from the center of the weld. So if it is an welded section, welded batten plate like that, So from here to here is the S. So this is 220 and this overall is total 60. Okay, this overall is total 60. It will be the 60 by 2 here, and here will be also 60 by 2. So getting 2 into 60 by 2, here 60 by 2, here 60 by 2. So 2 into 60 by 2 will be equals to that value. So 83.93 kilonewton will be the value of that. So moment will be equals to Vt by C into N. So value of the moment will be the value. Putting the formula, we are getting the value. Now shear stress, as the shear stress depend upon the D, that is the depth of the overall depth. So two values of the shear stresses and two values of the two values of the shear stresses and the bending stresses will be determined. The shear stresses for the N Batten formula, putting the value, what is the formula for putting the value, that is equal to Vb by Un. Vb is equal to, we are getting the value, Vb is equal to 83.93, so 83930 divided by A1, that is equal to T into D. T is equal to 10 mm thickness into D is equal to, we are getting for N Batten, D is equal to 270. We have determined the N Batten, the D is equal to, for N Batten the D is equal to 270. So value will be equal to 31.1, which has to be less than Fy by root 3 comma W, that is 131.2. So condition satisfied. Intermediate Batten 83.93, 10 into 205. For intermediate Batten we have got the overall depth 205. So 205 we are putting the value. So we are getting 40.94, which is less than that. Now coming to the bending stress. N Batten, what is the formula of bending stress? 6m by Td square. So 6 into moment, we have calculated the moment to be that. So 6 into m by 10 into d square, Td square, T into d, that is the d for the N Batten and t for the intermediate Batten. Putting all the values and all the conditions are satisfied. So hence okay. So provide this Batten and this Batten to be the N Batten and intermediate Batten. Now coming to the connection design. Now it is a welded connection, so will be designed as per that thing. Now as we do not know the thickness of the weld, we have to determine the thickness of the weld. The thickness of the weld we have to determine. So taking the thickness of the weld is equal to T. Throughout the process we will take the thickness of the weld is equal to T. At the final we will get the value of the thickness. Now direct shear Q1 is equal to longitudinal stress by effective area of the weld. Now longitudinal stress providing, now assuming welds are provided at like this all four sides, okay, like this all four sides. So Q1 will be equals to the longitudinal stress that we have calculated longitudinal stress to be 83.93. 83.93 is the longitudinal stress. 83.93 divided by 2 into overlap, that is 205 plus 60, 205 plus 60, 205 plus 60 into 2, that is the length of the overlap. It is 205 plus 60, 205 plus 60 the overlap value. This is 60, this is 60, this is 205, this is 205. The total is the value of that into T. We do not know the value of T, so putting in the value of T. So now providing for intermediate Batten. Now as the value of the intermediate Batten overall depth is less, so the critical value is that value because this is a lesser value. So if this get successfully passed, say N Batten will also automatically will be passed. So we are getting the value for overall depth for that value on intermediate Batten. Now coming to the shear stress due to moment, that is equal to m by m into r by ip. Ip is now r. What is the value of r? R is equal to that value, that is formula is equal to a by 2. Here the formula is written, that is a by 2 whole square plus d by 2 square. So value will follow along, getting the value of 106.8. So and now ip is equal to the polar moment of inertia. Polar moment of inertia for the weld section. If this is 205, if this is 60, iz will be that value. If you I think you all know that, so you can calculate that. Okay, this is by using the parallel axis theorem. Similarly Iy for the weld you can calculate by using parallel axis theorem. We are getting the ip iz equals to 269.67 into 10 to the power 4, okay, and 269.67 10 to the power 4 plus 40, and Iy is equal to 40.5, okay. Now so long ip will be equal to 310.17 10 to the power 4. Similarly q2 will be equals to, what is the value of q2? Q2 will be equals to m into r by ip. So value of q2 is equal to that value, so m into r by ip. Now combined stress value is equal to that. Now theta, now coming to theta, cos theta will be equals to, now cos theta will be equals to a by 2 by r, that I have shown you that it is a by 2. Cos theta is equal to, theta is the angle between r and horizontal angle, so this is a by 2 and this is r. So base by hypotenuse equals to cos theta. So base by hypotenuse cos theta. Okay, if we see the diagram, this is R, this is D by 2, and this is A by 2 in this picture. If we rotate it like that, and this is the value of theta. Okay, so if we rotate it like that, so cos theta is equal to so 0.281. Now it should be 156.36 by t square q1 square. We have got the value of q1 as that. Okay, we got the value of q1 is equal to that value. So q2 square, putting all the values and calculating that, taking the t square in the outer section 1 by t, it should be less than the fu by root 3 gamma m2. Now for shop welding, for site welding, the value of the gamma m and w is equal to 1.5. so gamma mw 1.5, it will value is equal to 157.81. so after getting all the calculation done, it is 472.95. so t is equal, should be greater than 2.99, providing a 5 mm site weld to make the connection. So this is the design of the connection. So up to this is the design of the connection and the design of the batten plate. So throughout our lecture, it is a very long lecture and very long video, because it is the most important part. Many maths come from this lacing and batten design. So this is the two examples that I have discussed. I have given you one assignment also. So throughout our lecture, we have seen that the lacing and battens are designed in numbers of way, in batten, intermediate batten, and also the lacing. So please, in your exam, follow all the steps and do the math properly. Okay, stay home, stay safe, for you know all the conditions. Okay, thank you students for your time.